The second lecture, the third lecture of ring theory. So in the last lecture, what we have defined, integral domain, zero divisors and units, right? So in the last time I made a mistake, I guess. So what was the units in Z4? Just a second. What is this? Yeah. So in Z4, what are the units of Z4? Z4 means 0, 1, 2, 3, right? What are the units of Z4? So units of Z4 is actually, I did today's empty, but no, there will be 1 is a unit of Z4, because for 1 itself is a B, just that 1.1 is 1 of Z4, right? So 1 is a unit, so unit of Z4 is actually 1, is a singleton 1, right? So yesterday I did a mistake, I guess, right? So I don't know, yeah, this one, right? So this will be, there will be 1 in the last lecture, because for 1 there is 1 such that this is 1. So no other element will be an unit, right? This you denotes the units of units, right? So today we'll discuss some more things, that division ring. First I am writing the definition of division ring. What is a division ring, right? So division ring, it is division ring, okay, or it called a skew field. What is happening? Division ring or skew field. Both are same, so I guess I should, yeah, division ring or skew field. What is this? A ring with unity, a ring, it should also be 6, a ring with unity, a ring with unity is called a division ring, ring if every non-zero element is a unit, right? A ring with unity is called a division ring if every non-zero element is a unit, right? What are the examples we have seen in earlier? This kind of every non-zero element is a unit. So examples are something like q plus dot, okay, and r plus dot, okay. These are every non-zero element. For any a you will get only 1 by a, such that it will be 1, right? So a cannot be 0. So a dot 1 by a will be a dot 1 by a equals to always 1 whenever a is non-zero. So every non-zero element of them are a unit, right? So this is the definition of division ring, or it is also called skew field, right? So what is the definition of field? What is a field? F-I-E-L-D. In terms of ring, a commutative division ring is called a field. A commutative division ring is called a field, right? a commutative division ring is called a field. And we know there are other some definition of field, which is in terms of operations. So I am not going to talk about like this, because I am in ring theory course. I will strictly follow the notation of ring theory. A commutative division ring is called a field. So division ring as well as it is commutative, right? Commutative means it is commutative under the second operation, right? The first operation is always commutative because it is abelian group, right? So there is no meaning of talk about the first operation. There should be, this should be commutative with respect to the second operation. Okay, this is called a field, right? These two definition is clear. Okay, so today we'll start now ring of integers, right? Ring of integers. So ring of integers, ring of integer, that means we'll talk about z plus dot. What are the properties of them, or what is the properties of this ring, and we'll discuss those kind of things, right? So z plus dot. So the first property, I'm writing the properties of it, and I'll write the property as well as the explanation. So you know that z plus dot is a CRU. It is a commutative ring, of course, and with unity. There is unity element 1, unity element 1, right? This is a commutative ring with unity. This is called CRU, right? So 1R is inside Z, and it is commutative A dot B is equals to B dot A for every A comma B inside Z, right? So this is CRU, right? This is commutative ring with unity. The second property I am going to write is what are the units of Z? We have, what are the units of Z? Uz means the units of Z. See, for unit you have to, for every if you have A is called a unit if there exists B such that A dot B is 1, right? So what does it mean? That if you take 1, then only you will be able to choose B to be 1, you will get 1. If you take A to be minus 1, you take B to be minus 1, right? You will get it 1, right? Minus 1 into minus 1, you will get 1. So can there be any other element except A? Suppose A is not 1, minus 1. So A dot 1 by, sorry, A dot B. So will it be 1? It is not possible at all, because suppose you have taken 3 or 2, so you should have to take 1 by 2 as B, that then only you can talk about 1, it will be 1. But 1 by B, 1 by this is 1 by 2 is not a member of Z. This is not a member of Z, so you cannot take this. So your only choices for A is 1 and minus 1, right? So there is only 2 units of Z. This is only 1 and minus 1 units of Z, right? So is this clear? Is this clear? Yeah, it should be clear. So the third property I am going to talk about, what are the idempotents in Z? Idempotence means A square, it should satisfy A square equals to A, right? A square equals to A. So 0 square is equals to 0 and 1 square equals to 1. It always satisfies. But can there be any other element? No. If you take any A square, it will not be A, because you see here A, you can take A minus 1, this is 0. Possible choices of A and A minus 1 are either A equals to 0 or A equals to 1. So there is no other element except 0 and 1, right? So idempotents which satisfies A square equals to A. So idempotents are 0 and 1. There is no other idempotence element inside the inside the field ring Z, right? Okay. So this should be clear. And the fourth property I'm going to write. What are the zero divisors? Z of Z. Z means the zero divisors, right? What are the zero divisors of? What is the definition of zero divisors? A inside Z, right? Such that A is non-zero. You can write it to be here, I guess. A should not A inside Z minus 0, such that A dot B is equals to 0 for some B inside B inside Z minus 0, right? So you should have two non-zero element, and you multiply it is 0. Is it possible in Z? Is it possible in integers that if you multiply two non-zero integer, it will give you 0? Is it possible at all? There is no possibility, because A dot B equals to 0. A dot B is equals to 0 is implies that either A equals to 0 or B equals to 0. There is no other choice. So one of them must be 0. So this property, so this is not satisfying any A inside the Z, right? So my claim is this is empty set. There is no, right? After that we'll talk about one more property. This is the okay. One, we are lifting out with one, which is what is the nilpotent element in Z? What are the nilpotent elements in Z? Nilpotence mean you should have an A, so that A keep over some K. This is 0. So 0, definitely 0 will satisfy this. A equals to 0 satisfy this in Z. But can there be any other element which satisfy A dot whatever you multiply, this is 0? It is not possible in Z, right? If you multiply any non-zero integer, it will not give you 0, same integer. Okay, so it is actually 0 is only satisfying this, right? Have you got? Okay, the sixth property. What are the properties it is remaining? Okay, what is Z is an integral domain? So Z plus dot. What is the definition of integral domain? First of all, you should have to be the last lecture what I have told about the integral domain. If you have for a commutative ring with unity, if it has no zero divisor, then we call this is to be an integral domain. But what are the zero divisors of this? Zero divisors, this is empty, right? So there is no zero divisor. So by definition, it is an integral domain. So Z plus dot is an integral domain. So Z plus dot is an integral domain ID, right? So because Z plus 1 has no zero divisor, and what is the definition of integral domain? If it has no zero divisor, R plus is commutative ring with unity said to be integral domain if it has no zero divisor. And Z plus dot has no zero divisor because the set of zero divisors is empty. There is no zero divisor. That is why this is an integral domain, right? So this is yeah, the 7 properties. Is it a division ring? Because a ring with unity is called a division ring if every non-zero element is an unit. But what are the units of here? Units here. Units is plus minus 1. So but other elements are not unit. So if every non-zero element is an unit, then we say that what are the units? These are the units now. If every non-zero element is an unit, then we say called Z is a division ring. So this ring is a division ring. But here only plus 1 and minus 1 are the division rings. Rest all are not are not units, right? That is why this is not a division ring. So z plus dot is not a division ring, right? So these 6 properties is for z plus, and rest properties we'll discuss after studying enough, right? So these are the basic properties of z plus, right? Ring of integer, this is z plus. Now we'll define a subring. What is a subring, right? So subring, so what is a subgroup? The similar kind of things here is subring, right? So that means this should be a subset of R. So a non-empty, there is no need to non-empty, I guess, but in definition they have given is it is not S to be non-empty. A non-empty S be a non-empty subset of R, be a subset of ring R, then S is called a subring of R plus dot if S plus dot is a ring itself. If it is itself a ring, then we say this is subring, right? The similar kind of things. There is no, first of all this should be a subset, and the okay, what is happening? Yeah, it is a subring itself. Then which one? S is a subring, right? What is the criteria for subring? What is subgroup? What is the subgroup? Criteria for subgroup. A subgroup is H is a subgroup of G if one for any a comma b inside H, a minus b or a b inverse if it is H, then we said H is a subgroup, right? So for similar kind of things will happen in subring, right? So criteria for subring, criteria to check for subring, right? Criteria for subring is, suppose S is a subset of, not this is ring, I'm real number, so R plus dot, right? S is, if is a subset, S should be non-empty, is a subring, if and only if, these are the equivalent definition, if and only if the first property should satisfy that S plus is an abelian group, right? What does it mean? It is equivalent to saying that S plus is a subgroup, S plus is a subgroup of R plus, is a subgroup of R plus, right? First of all, what is this? Yeah, S plus should be a subgroup of R plus, and the second, S comma dot, the same properties for ring, S plus dot is a semi-group, right? Equivalent to saying that this is actually semi-group means binary operation plus associative, which is equivalent to saying A dot B is inside S for all A comma B inside the ring R, sorry, inside S. So for all A comma B inside S, this is an abelian group. First of all, this should be an abelian group, and this is a semi-group, the same definition. An abelian group means the S plus should be a subgroup of R plus, right? S plus should be a subgroup of, because any subgroup of abelian group is abelian. So any subgroup of abelian group is abelian. So similarly, S plus is also abelian. So S dot is a semi group, that means binary operation plus associative. That means that A dot be inside S. Okay, for all A comma B. This is the criteria for subring, and you must two criteria together, then you will get the subring, two-step test for subring. So I'm writing here two-step test for subring. That means you have to check for two step, and you will get whether it is going to be subring or not, right? So S is a subset of R, where R is a ring, S is a subset of subring. Okay, S is a subset which is non-empty, is a subring of R, is a subring of R if and only if equivalently, first of all, A minus B should be in S, and second of all, A dot B inside S. This should happen for every A comma B inside S. If this two property satisfies, then we say that S is a subring of R. Okay, here you can conclude that it actually means that equivalently saying that A minus B is inside S, because this is for subgroup test. Okay, for every A comma B inside S, you can write it here. So just I am to merging this and this. So what is the test for subgroup? Subgroup means A minus B or A B inverse. B inverse is actually A minus, so you can write it A minus B or A B inverse inside S. So this two property is satisfied, then we say S is a subring of R. Okay, that's it, nothing else is here. Okay, so now I am going to give some examples. So let me give an example. Okay, examples, whether verify, you may verify that, suppose R is my 2 cross 2 matrices over Z. Suppose R is actually A B C D, such that A comma B comma C comma D is inside Z with plus with dot, right? There are usual matrix addition and matrix multiplication is here, right? There is nothing else. So it is actually same as denoted by M2 over Z. The field is, sorry, the elements are coming from Z. Okay, this ring. Define a set S. S is, suppose S is A B C D, such that the determinant of this, that means AD minus BC, is equals 1. Clearly this is a subset of R, this is, which is actually M2 over Z, right? It is clearly, it is subset of this is contained in here, right? So can you please verify that S is a subring? Verify whether S is a subring of R or not, right? Okay, so can you please verify? So let me verify. What you have to check just two property. Just first one is saying that a minus b, you take two elements, suppose a1 comma a1 b1 a1 b1 c1 d1 and a2 b2 c2 d2 some member of r, which is actually m to z, right? So you have to check whether this the suppose this is a, suppose this is b. So a minus b, what is a minus b? Which is actually a1 minus b1 a2 b1 minus b2 c1 minus c2 d1 minus d2. Okay, is it inside S? So for to this element should inside S, you have to check whether this determinant is 1 or not. Let me check, let check whether the determinant is 1 or not. So what does it mean? a1 minus a2, the determinant is d1 minus d2 minus b1 minus b2 into c1 minus c2, right? Which is actually equals to a1 d1 minus b1 c1 minus a1 d2 plus a2 d1 plus b1 c2 plus b2 c1 minus b2 c2, which is not equals to 1. Okay, which is not equals 1, which is not equals 1. So that means this element is not lying in Z. So this is the first condition, which is a minus b is not inside S. So this is by default, this is not a subring, right? The second property you don't need to check because the first property is violating, right? So and another way you can check also, you can check that suppose an element here, you take a and b to be 1 1 0 0, right? Because determinant is 1 clearly, and b, take b to be 1. And what is a minus b? A minus b is 0 matrix, right? 0 0 0 0. The determinant of this is, determinant of a minus b is 0, so it is not inside. So this element is not inside S. So this is not closed under the first operation, so we cannot talk about whether, so this is not going to be a subring. Okay, so what else? Okay, this is not a subring. Let's check whether what are the subring, what can be the subring of them. So suppose I am defining, suppose this and S2 I am defining, right? Just okay, suppose S2, I am giving S2, which is actually a b 0 0 inside R. That means whatever R I have chosen M to Z just earlier, this R, right? This R, I am choosing element from here such that a comma b inside Z, right? Such that a comma b inside. Is it a subring? S2 is a subring of R. Verify, please verify it, because this is not so difficult to verify, right? So let me take two element A, which is actually a1 b1 0 0 and b to be take to be a2 b2 0 0. Clearly a minus b will be lying in S2, because this component will be definitely 0 and this will consider some elements of Z, right? So this is by default. You have to check the second property whether this is verified. So you take a dot b, a1 dot b1. What is this? a1 b1 a2 b0 0 a2 b2 0 0. What is this? It is a1 a2 a1 b2 0 0. So this is a member of S2, right? Clearly there is no element of subdeterminant. This is clearly of this form, right? Suppose you take this to be some a dash b dash 0 0 a dash b dash b dash inside z, right? So this is clearly, these two properties clearly this is satisfying, and a1 dot b1 is inside S2 is also satisfying, right? So this is a subring. Okay, so clearly you can verify, you may verify that one thing. So I'm giving you S3, suppose S3 what is S3? I'm giving you a b 0 0, such that a comma b, it is actually m to z, inside m to z, whatever the I have taken the z, okay, so that a comma b is inside z. A similar thing, is it a subring of R? Verify. It will be, and you verify it in yourself, right? I'm not going to. So one observation here, so Z is a subring of Q. This is the notation for subring, okay? For subgroup also, and as a subring it is a notation, right? A subring of Q is a subring of R, and this is a subring of C. So all the operations are addition, usual addition and usual multiplication, right? Okay, Z is a subring of Q is a subring of R is a subring of C, right? So okay, so now subring is over. This is enough for a subring, right? And let me so introduce something new. Just in the first lecture we have we defined the power set of natural number, right? So power set of natural number means power set of natural number, right? So my point is, while analyzing power set of natural number with respect to symmetric difference and intersection, right? Okay, we know zero element, what is the zero element is actually empty set, and unit element is actually the entire natural number, right? 1R. So the first property I am going to write, this is the first property, and I will write the properties as well as the explanation of them, right? So you can note, so power set of natural number with respect to symmetric difference and intersection is a CRU, right? Is it why this is so? Because the unit element is this. 1R is an unit. You can verify that 1R is an unit because you take any element, and what are the unity element in, that means the identity element with respect to the second operation. That means you take any A, you must have any B, such that this is going giving you A, right? This is the where B is, you take B to be natural number, so A intersection natural number, it always giving you A, because A is a subset of natural number. A is contained in natural number, it will definitely give you A, right? So N is a unity element here, unity element, right? N, the entire entire natural number is an unity element, right? So is a CRU. And why this is commutative? Because you take intersection A intersection B is equals to B intersection A. Obvious. B intersection A, this is commutative. I am again saying the commutative with respect to the second binary operation. This is intersection. So A intersection B and B intersection C are precisely same. So this is a commutative ring with unity is called a CRU, right? What else? The second property what are the units of power set of natural number? So units of power set of natural number, this set is actually called units, right? So for unit A should be non-zero, that means A should not be empty set. And suppose A dot B, this is actually 1R. 1R means 1R. 1R means here n. Okay, A dot B means key. A dot B means A intersection B. This is actually n, right? A intersection B is n. When it will happen? If and only if. It is only happen when A is equals to B equals to n. There is no other choice. What is the definition of a unit? Unit means you just, for every element A, for A, if there exists an B, for any A, if there exists an B such that A dot B equals to 1R, then we say that A is unit, right? So for A, so you have to choose for A intersection B equals to n, you have to choose A to be B to be n. There is no other choice in your hand, right? So the units of power set of natural number is only natural number n. There is no other choice, because there is no other choice. If you take B to be anything, so your B has to be n, right? There is no other choice, because you have to intersection should be the entire natural number. So it is only happen, it can only happen if and only if your A and B both are natural number, then only your intersection will be entire natural number, right? So second property, is it clear? The second property. Okay, so I'm writing the third property right now. Okay, the third property, what it says, similar thing I will, whatever I have did in Z. What are the zero divisors? For zero divisors, see, A with respect to second binary operation, which is B, A intersection B should be empty. Zero means empty, na? So A intersection B should be empty, and A should not be zero, B should not be zero. That means A and B both are non-zero element. You have to talk non-zero element. That means A is non-empty, B is non-empty, and you have to talk about A intersection B is empty, right? So what are the choices? What are the choices for A and B? So okay, and for the zero divisor, A should be non-zero and non-unit element, right? So A cannot be equals to, what's happening here? A is empty, and A is also non-zero, non-unit, because unit n is a non-unit element, right? A should be non-zero, non-unit. So non-zero means non-empty, and non-unit means A should not be n, such that A intersection B is empty. What are the choices in your? So always exists B to be A intersection A complement. You take B to be A complement, it will give you empty set always, because if you have the universal set here, if you have A is here, this is A, the A complement is this, right? Except this circle. So always A with respect and A intersection, this will be empty. So if you have any A, you choose A complement, you will get empty set. So this is the choice for B, right? So power set of natural number will be, it will be everything except so it will be entire power set of natural number, except empty set and natural number, right? Because power set of natural number, zero divisors are actually power set of natural number, because A should be non-zero and non-unit element. So okay, So it should be non-zero and non-unit element. So non-zero non-unit means this should not be 0, this is not, it should not be n, it should not be 0. So every element, so you take any element a or you intersect with a complement, you will get empty set, right? This is why the power set of 0 divisor the power set of natural number except this two, right? Okay, what else now? And the nilpotents, this is 4 nilpotents of power set of natural number. What is it? Nilpotents mean if you have a intersection a, that means a की power k, that means a intersection a dot 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 intersection a should be empty. What is the choice for a? It is empty if and only if a is empty. There is no other choice. A की power k, which is 0. 0 means here empty set. So a की power k is empty, that means a की power k with respect to intersection. This implies that a intersection a dot 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 a is empty. That means that it only can happen if and only if a is empty. There is no other choice. You have to choose the same element, na? So this is why this is an empty set. Is it clear? Only 0 element is a nilpotent element, right? 0 element is a nilpotent. This set is not empty. Empty set is an element here, right? Okay, this set is not empty because empty set, that phi is an element. This is not empty set. This is not this. Okay, so there is singleton set, right? Okay, nilpotents. What are the idempotents? Nilpotents has been over, so left out with idempotents. Idempotents of power set of natural number. So for idempotents, a square equals to a should. So the a square means a intersection a is a. So it is true for every a. For every a it is true. So this is actually the entire set power set of natural number will be. Okay, is it an integral domain? So for integral domain, every non-zero element should be an unit, but here n is an unit, right? Unit is n. So every non-zero element, if it is unit, then we say it is integral domain. Okay, what is the definition of integral domain? I just mentioned lecture number 2, I guess. Yeah, 2. So the choice is in your so every non-zero element should be an unit, right? But here it is the unit. What is the unit of power set of natural number? Unit is, there is a singleton n, na? Singleton n is an okay, sorry, I guess there is a confusion. So this is actually, I am talking about whether it is an integral domain or not. So what is integral domain? So it is commutative ring with unity, of course, but it is commutative ring with unity is said to be integral domain if it has no zero divisor. What is a zero divisor? The zero divisor, there are infinitely many zero divisors. Power set of natural number with except 0 and n. Okay, there are many zero divisors. So if there is no zero divisor, then we say this is an integral domain. But this is not an integral domain. Not an integral domain. And the sixth property I am going to talk about, whether it is a division ring or not. It is also not a division ring, because for division ring, every non-zero element is an unit, right? A commutative ring with unity, a ring with unity, any ring with unity, division ring, if every non-zero element is an unit. But here only unit element is n, so it is not a division. Those two are by definition. Okay, by definition. And these are some properties. These are some properties of power set of natural number with respect to symmetric difference. Okay, these are some basic properties of it. Okay, and later on we will discuss some more properties, and till for now this is enough. So I'm giving you a question. Question is, what can you say about idempotence of a ring intersection nilpotence of a ring intersection nilpotence of a ring nilpotence of a ring? What can you say about the idempotence of a ring, of this ring, and nilpotence of this ring? So I'm giving you one process, one argument, one side, and you will finish in yourself. So let's suppose A be an element of intersection n of r, right? IR intersection n of r. That means the IR of means, what is the I of r? I've just defined that this is the nilpotent, this is the idempotence. The A be an element which is also nilpotent, also idempotent. What does it mean? This implies that A square equals A, and idempotence, for idempotence A square equals to n, and A ki power k is 0 for some k, right? K inside natural number. So we have A square equals A, right? You multiply A ki power k minus 2, A ki power k minus 2 into A square, which is equals to A into A ki power k minus 2 into A, whatever, A ki minus k minus 2 into A. What is it? This is A ki power k, and which is A ki power k minus 1. This implies that. And what is this? A ki power k is 0, which is A ki power k minus 1. The A ki power k minus 1 is 0. Okay, A ki power k is 0 na, because this is A ki power k is 0. So A ki power k minus 1 is 0, right? So similarly, you will do A square equals A, which is, this implies that A ki power k minus 3, A ki power k minus 3 into A square will be A ki power k minus 3 into A. It implies that A ki power k minus 1 equals to A ki power k minus 2. What does it mean? A ki power k minus 1, we have just defined this is 0. This implies that this 0 equals to A ki power k minus 2, right? Because A ki power k minus 1 is 0. So repeat the same process, you will get every A is 0. You will get every A is 0. Repeat the same procedure. Repeat the same procedure. You will get finally A to be 0, right? So IR intersection NR nilpotent of R for any ring. I am not defining here power system natural number, or for any ring it is always 0, right? For any ring IR intersection NR is always 0. So the argument is here, you can proceed like that. For A square is A, I am A ki power k minus 1 0, A ki power k minus 2 0. Similarly, I will say that A ki power k minus 3 is 0. Similar process I will repeat. Similar, and I will say A ki power k minus 4 is 0. Okay. Similarly, you will get A to be 0. Oh my god, what is this? Just a second. Yeah. So you will get A ki power k minus 3 is 0. Similarly, you will repeat the process, you will get everything. Okay, I think it should be clear. It should be clear to you, right? So this is for today, and I am giving you one exercise for you. So what can you say about similarity? What can you say about units of R intersection idempotence of R? You just use the definition of it. Suppose you have taken one element here, this so it will of course a unit, also an idempotent element. What can you say about this? Okay, we'll discuss it in the next lecture, and you just try. It is very easy. You just use the definition. You take any element here and here, you will get what is actually happening, right? So this much is for today. I'm ending the lecture here, and we'll discuss this problem in the next lecture, right? Thanks for watching.